Hello, my dear students, and as I started your complex analysis and integral transform, on the last lecture I started this topic in which in complex analysis I took up the topic analytic function. I just introduced this topic analytic function on the last lecture, that is lecture number 1, and now I will continue this in lecture number 2. On the last lecture 1, I introduced analytic function, and in which I told you what is complex number and then what is a complex function, and I told you complex function means a function of u plus iv, means a function of two variables here, u and real part, and it is also a function of two variables. V is its imaginary part, it is also a function of two variables. And then I told you what are the calculus characteristics of this function, in which first I told you what is the limit of complex function f(z), what is the continuity of complex function f(z), and then what is the differentiability of complex function f(z). After defining these characteristics, I introduced analytic function, and then I told you what is analytic function, means definition of analytic function at a point, definition of analytic function in a domain. Definition of analytic function at a point, I told you a function is said to be analytic at a point, at any point, if it is differentiable not only that point but also in the neighborhood of that point. Means for analyticity, function must be differentiable at that particular point as well as in the neighborhood of that point. And second definition, what is the definition of analytic function in a domain? Then I told you a function, if a function is differentiable at all the points of a domain, if we take a domain that is a set of number of points, if a function is differentiable at all the points of this domain, then we say that this function is analytic in a domain. Alright, and I also told you there are two another names of the analytic function. One, I told you analytic function is also called regular function, and second, analytic function is also known as this analytic function is also called as regular function. Second, I told you this is also known as holomorphic function, right? And in all the introduction, I told you here we are taking complex function fz because I told you z is a complex function, means it is an ordered pair of real number. So here we are dealing with the function of more than one variable, means we are dealing with the function of two variables. So all the concepts of the checking of existence of limit, checking of continuity of function, checking of the differentiability of function will be changed. And if we take differentiability, and I took one example, you know that how you can check the differentiability of a complex function, means function of two variables. Then I told you here different derivative means if we take derivative of this function, then derivative of this function means existence of this limit. If we take this limit like that, if this right hand limit exists, then we say that function is differentiable. And here every function is a function of two variables. So concept of existence of this limit on the right hand side is slightly different, and that method is that because in single variable you know that we check the existence of limit by taking left hand limit and right hand limit. If both limits exist separately and both are coinciding, then we see that limit of a function exists. But here, in case of function of two variable, as I took the example in the last lecture, we have to check the limit along the path. There are the various paths because we take here z plane, x-axis, y-axis, here x-axis is the real axis, y-axis is the imaginary axis, and also we can take some radius vector like y equal to mx. Also we can some path from the given function, if limit is independent of these paths, then we say that limit exists. And if limit exists, then we say that f dash z exists. And then we say that fz is differentiable at particular point. Up to this point, I have discussed in the lecture 1. Now, today, let's discuss what are the methods, what are the conditions by which we can check given function is analytic or not. For that, there is some necessary and sufficient condition for a function to be analytic. First, I discuss what are the necessary and sufficient condition. This is necessary and sufficient conditions for a function to be analytic. First, I discuss this condition, and these conditions will be used to check whether given function is analytic or not. What is the condition? If we take function fz equal to u of xy plus I times v of xy, then necessary and sufficient condition means if this function is analytic, then partial derivative of del u by del x, del u by del y, del v by del x, del v by del y exists, and del u by del x equal to del v by del y, and del v by del x equal to minus del u by del y. Alright, these conditions, actually these are the condition by which we can say that given function is analytic or not, and these conditions are necessary. Means if and only if these conditions satisfy, then given function is analytic. If function is analytic, then these conditions satisfy, and in which these two equations, del u by del x equal to del v by del y and del v by del x equal to minus del u by del y, these two conditions are known as Cauchy or Riemann, or in abbreviation CR equations. Cauchy-Riemann equations are CR equations. Means by CR equation we can check, we can say a given function is analytic in a region or given function is analytic at a point. First, we prove this necessary condition. If a function is analytic, then how these equations satisfy. So this is also a proof of necessary condition, or you can say proof of CR equation. First, we prove this mathematically. CR equations. How can we prove this? If given that fz equal to u of xy plus I times v of xy is analytic in a region, then we have to prove that if these derivatives exist and satisfying these two equations, and these two equations are known as CR equations. If we take for partial derivatives, for existence of derivative, if we take del x and del y be some increment of x and y respectively, and del u, del v and del z are be same for u, v and z respectively. Then we know that z equal to x plus iy. So del z equal to del x plus del iy. And we take what is the definition of here fz. Then by standard formula f dash z, you know that limit delta z tending to 0 f of z plus del z minus fz upon del z. This is the definition of derivative, and if we open this, this is limit del z tending to 0. This is u of x plus del x y, that is u of del u plus I times v of del v. This is u plus iv upon del z. If we separate the real and imaginary part, this is, you just cancel out, that is del u plus I times del v upon del z. Take this as equation number 1. If function is analytic, then by the definition of analyticity, I told you if function is differentiable in entire region. And if function is differentiable, then the value of f dash z exists, means this value on the right hand side of the equation 1 exists, means, and here again function is of two variable. So existence means the value of limit is independent of all the path taking for the value, finding the limit of limit. So first we take this, since fz is analytic, so f dash z exists, and so limit del z by del n 0 del u by I del v and del z, this exists. Right? Now first take limit del z and del 0 along path real axis. Real axis means x-axis. Then del z equal to del x and del z tending to 0 means del x tending to 0. So from equation 1 we get f dash z equal to limit del x tending to 0 and delta u I delta v upon delta x. After taking limit, we get del u by del x plus I del v by del x. Take this as equation 2. This is the value of limit along the real axis, means value of limit along one path. Now take value of this limit along another path. That is, now we take the limit along imaginary axis. Imaginary axis means y-axis. Now take limit del z tending to 0 along imaginary path, that means y-axis, and so del z equal to I del y and del z tends to 0 means del y tends to 0. And so from equation 1 we have f dash z equal to limit del y tend to 0, and here del u plus I del v in place of del z, that is I delta y. And take this separately, we get del y tending to 0, del u upon I del y. I is cancelled out, limit delta y tending to 0, delta v upon delta y. This is 1 upon I del u by del y. This is delta v upon delta y. And we know that 1 upon I means minus I. If we take the rationalize this after multiplying I in numerator and denominator, then we get this, because we know that I square equal to minus 1. And then so it is equal to del v by del y minus I del u by del y. Take this as a equation 3. If function is analytic, then it is differentiable. Limit exists, and limit exists because f dash z exists. So by equation 2 and 3, we get del u by del x plus I del v by del x equal to del v by del y minus I del u by del y. Means limit is independent of the path. So value of limit along the real axis, value of limit along the imaginary must be same. And now taking real and imaginary part, will we get del u by del x equal to del v by del y and del v by del x equal to minus del u by del y. And that is your proof. These are your CR equation. Now necessary condition is proved. If function fz equal to u plus iv is analytic, then these equations satisfy. Means del u by del x equal to del v by del y and del v by del x equal to minus del u by del y. These are the sequence CR equations, means Cauchy Theorem equations, and this is your necessary and sufficient condition for any function to be analytic at a point. And this is the basic tool and main tool by which you can check the given function is analytic or not. Now, for the other part, yeah, you can say in other way, you can explain how we can use these CR equations to check the analyticity of the given function. We can take numerical examples, because in a function, how you can check given function is analytic and not. So we take a numerical example. Example is show that function fz equal to e to power x cos y plus I sin y is analytic, and find its derivative. If we take this example, then by this example, your concept more clear is that if any function is given and you have to check whether it is analytic or not, then you can check by the help of CR equation. Take solution of this equation. If you compare this function by your standard form, fz equal to u plus iv, so here u equal to ex, that is real part, and v is equal to ex sin y. Now first you calculate all the partial derivatives of u and v with respect to x and y, and then we see that we check that if CR equations are satisfied or not. Then here, if you calculate partial derivative del u by del x, that is ex cos y. Partial derivative of u with respect to y, that is ex, and minus cos y means minus sin y, that is minus ex sin y. Now take partial derivative of v, del v by del x equal to e to power x sin y, del v by del y equal to ex, and sin y partial derivative is cos y. These are the derivatives. So here we get del u by del x equal to del v by del y, these two, and del u by del y equal to minus del v by del y. That means CR equations are satisfying. Hence, Fz is analytic. Right? Fz is analytic. If Fz is analytic, then you can say that Fz is differentiable. Right? By this property, you can find the value of second part of the question. That is, find its derivative. When function is differentiable, then you can find derivative directly, because if it is differentiable, then we know that f dash z means del u by del x plus I del v by del x भी ले सकते हैं, right? Or you can take like that del u by del y plus I del v by del y, means you can take partial derivative either with respect to x or with respect to y directly, and you have the value of this del u by del x means ex cos y, I times del v by del x means ex sin y. Substitute the values of partial derivatives and take ex as common, we get cos y sin y. Ex, this by Euler's theorem, it can be written as e to power iy, powers adding, then e to power x plus iy means e to power z. This is the derivative of function, that is the answer of the second part of the question. Means by CR equation, in similar way, in this way, we can check given function is analytic or not at the region. Now, I will take another example in which function is given and discuss the analyticity of the function for the various path. Means it is not analytic in entire domain, in entire region, but in some particular point it is analytic, but other points it is not analytic. So here we take another example by which you clear more concept, and that example is discuss the analyticity of function fz equal to mod z square. Mod z square unit, it can be written as also zz bar, right? Another statement of this question, that is very important statement in semester examinations, in some examinations also stated this question in this way, that is, prove that the function fz equal to mod z square is continuous everywhere, but nowhere differentiable except at the origin. This is another statement of this question. Fz equal to z square is continuous everywhere, but nowhere analytic except origin. Means in the decision of analyticity of this function, we have to discuss, we have to prove two things. One, function is continuous everywhere. Second, function is differentiable at origin only. Means function is, you can say, function is analytic at origin only. So, how we take this, how we solve this question, and by the solution of this question, also, if you have any doubt about definition of analyticity our theory of analyticity, then I think the solution of this question, this doubt will be cleared fully. What is the solution of this question? Here, function is fz equal to mod z square. You know that here z equal to x plus iy, and we know that mod z means under root x square plus y square. So this is x square plus y square, right? This is purely real function, means we can write it as, or if we compare its by original function fz equal to u plus iv, so here u is x square plus y square and v is 0. Now, if you see here function of u and v, so this is 0, this is a constant function. This is a polynomial of 2 degree. So by the theory of polynomials, directly we can say that here u and v are continuous everywhere, because it is also constant function. Constant function is always continuous. This is a polynomial of degree 2, x square plus y square, and you know that polynomial is also continuous everywhere. The first part of the question has been proved. The function is continuous everywhere, because u and v continuous, that means fz is continuous everywhere. Right? Now we have to discuss about the differentiability of this function. For differentiability, if we take partial derivative, that is 2x, partial derivative of u with respect to y, that is 2y, although partial derivative of v is 0, partial derivative of with respect to y is 0. So by CR equation, we can see that del u by del x equal to del v by del y, and del u by del y equal to minus del v by del x, only at x0 and y0, means origin, only at this. So by this concept, by this theory, we can say that fz is differentiable by CR equation, or you can say that by necessary condition, we say that function is analytic at 0, 0 only. That means, you know that if function is analytic, then it must be differentiable. If function is differentiable, then it must be continuous. So we can say that fz is differentiable only at 0, 0. This is the answer of the second part of the question, right? So this is the basic concept by CR equation. Here we see that we can check also differentiability by the help of analyticity of the function. If function is analytic at any point, then it is differentiable at that point. But if function is differentiable, we cannot say it is analytic. But function analytic, then it is differentiable. This is the example, and this is the basic tool by CR equation, how we can check a given function is analytic or not. Okay, now in this lecture, I am just stopping this lecture on this topic, and next lecture I will discuss what is the properties of the analytic function, and this is actually CR equations Cartesian form. So they are also, you know that in coordinate system there is a polar coordinate system. So we discuss also what is the format of the CR equation in polar coordinate system. Okay, thank you.